Okay, we're just going to give a few minutes to let people sort of turn up. Oh. Just a show of hands, who here watched Kelsey's keynote talk this morning? Because I thought that was just absolutely fantastic. Not just because I'm a Fortran programmer. Can I just see who else here programs in Fortran? Yay! You do exist still. This is good. 20 years ago. That's still quite old Fortran. That was like at least Fortran 95, probably. Fortran 90, not bad. Most of my career at the beginning was Fortran 77. And yeah, we all have Fortran 77. It's one of the few programming languages older than me. And it's quite depressing, actually, because I teach students. And the students basically are now, some of them actually, next cohort will be the first students that were all born in the 21st century, which makes me feel ancient. But it means that basically languages like Python and Perl and C++ and all these are older than my students, whereas the only language I can find older than me is Fortran, so I kind of hold on to that. Oh, I'm going to try and be brave enough and run an online demo as well, which, you're gone?
Do you have music to play during your...
I'm an academic. We don't do rock star music. We do expect lots of maths, equations, and all of this stuff. Leave now, run in terror. I'm joking. I stripped all of that out. We have a nice fun, I've put code in there. So it's actually a weird conference for me. So I normally go to academic conferences. And so if I put code into a slide in an academic conference, the researchers run away screaming. So I've basically swapped all of my mathsy, quantum chemistry, stats, statistical thermodynamics slides with code slides, and I'm going to see what happens. It might work, it might not work, we don't know. But no, this is, again, a huge conference. Again, academic conferences, the ones I go to, typically we think it's a big conference if we hit about 150, 200 people. 8,000 is just mad. I don't know how we all meet each other, but I think a lot of us were down in the gardens last night. So I managed to go down to the gardens and at Mopop, and I was so thankful, and my wife's so jealous that there was the Marvel exhibition that was on. So there's like so many photos of the Iron Man costumes. I can see a few people thinking about still coming in. So again, if this was like one of my teaching talks or one of my workshops, we always give people 5 extra minutes, and I'm trying to teach students about the concept of timekeeping. And the way I teach my students about the concept of timekeeping is with social peer pressure. And so what we do is basically, once the timer started, we then basically all turn around and look at the people and stare at them as they come in through the door. And they begin to feel like socially awkward, and I'm hoping I'm doing you a favor, and they'll have learned this before they come and work in business. But typically, the students I come with, it's like if they actually come in earlier than 10 minutes before the start, I'm doing well. So it's the only way I can sort of try and fix this. Now we're at the time, so if you do want to now stare at people in the door, that will be fine. I will not mind. And indeed, since we have hit the time and I don't see anybody else walking, I'm now going to actually start. So, I am Christopher. I am an academic. And as I said, I really enjoyed Kelsey's talk this morning. And it wasn't just because of the Fortran. It was because what he said was really true. And that's that tech is brilliant. But actually, tech is not brilliant just as an end in and of itself. Tech is brilliant because it helps us solve the big problems. And as I said, I'm a scientist. I'm a research software engineer, so big problems are kind of most of my career. And the really big problems at the moment are happening in the life sciences. So I work in the life sciences, and what you see up on these screens, these are the molecules of life. These are the proteins, particularly these two, HIV protease and HIV reverse transcriptase. These are the proteins which HIV uses to take over your cells like the Borg, make your cells replicate more HIV and basically kill you. But now, science has advanced so much that we can understand how these proteins work at the molecular level. We can actually understand biology. We can understand disease at the molecular level. That's amazing. And what it means we can do is we can design molecules like the one on the far right. That huge molecule there is a designed molecule that we assemble. And that molecule contains antigens for lots of diseases with the plan that you can actually inject that molecule into people and it will be like a multi-target vaccine. Doing this kind of stuff, solving the big problems, is what I hope we're all here to do. And this is the end goal. This is what we want to do. Now, while our understanding of science and research has just advanced like anything over the last 50 plus years, the way that we use computers to conduct scientific experiments has barely changed actually since the moon landings. And indeed, thinking about hidden figures, they would actually recognize current modern high-performance computing because it looks kind of the same. You start off with a terminal, typically now on a laptop. They didn't have laptops back then. You describe your experiment on the terminal in text. You build all of the input data, and then you transfer it across to your big mainframe supercomputer. It's changed from being a big IBM, now it's a lot of Linux boxes. And essentially, you SSH onto the login node, you copy across all of the data for the simulation, and then when all the data is then on your mainframe, on your supercomputer, you then submit that job to the queue, because it's shared between lots of people. And the job then sits in the queue, it sits in the queue, it sits in the queue, it sits in the queue, and then eventually you get some nodes and it runs, and then the job will run for a while. We're doing these big, massive simulations. It will take a while to run, and then when it finishes, you'll log in, and maybe a week later, 2 weeks later, you'll check, and it's done. And then you'll copy all of the data that's been produced back to your little laptop, and you'll do more analysis in text. All those pretty pictures I just showed first, we don't look at those pretty pictures. They're just for papers and talks. We do everything in text. Now, that's terrible. If you think about all the advance we have in tech, we're still basically running on a 1970s command line interface to run the biggest, most important simulations that we actually do. What I would like to do is actually do science differently, and hopefully if the Wi-Fi works, I will show you what I mean. So while this is coming up, who here has heard of Jupyter? Yes. Again, scientific conference saying Jupyter, sometimes you don't really get anything. So you know that this is a Jupyter notebook. Jupyter is fantastic. It's running in the cloud. And so what we're going to do here is rather than be at our boring text interface, instead we're just going to basically execute command cells. And these cells are loading up the molecules that we want to simulate. So we've now loaded the molecules. We have here 631 of them. And now we're going to define the protocol with which we actually want to run the simulation. And now this line here, now we've loaded up the molecules we want to study. We know the protocol of the simulation we want to run. We execute that cell. It's now gone and run the simulation. It's burst it out. It's going. It's actually running a Fortran program. Woohoo. And now that that simulation is running, can I ask, is it actually running? Yes. How long has it been running for? It's been running for now 0.28 minutes. But it's live. Because it's live, I can inspect this simulation as it's going. So I can do things like ask, what's the energy of this molecular system as we're going now? Well, it's currently 6,000 kcals per mole. But now what's the energy? It's simulating, it's moving these molecules around, they're changing all the time. And we can then ask more than just the energy. We can say, how much time have you simulated? It's now done 52 picoseconds of simulation of this particular molecule. It's currently at a temperature of 28 Kelvin. The poor thing, it's very cold. But as the simulation progresses, it's now heating up to 37 Kelvin. We're interacting with a live simulation that's running on the cloud through an interface that researchers actually can use. They're not going to do Kubernetes stuff, sorry. kubectl is too difficult. But now we've got data that's evolving through time. I know scientists like to have text, but we can actually advance that to graphs. We do like graphs as well. This is now plotting those properties with time, and this is, again, live. So as I rerun this cell, it's going to pick up the latest data from the simulation and add that to the end. 2 dimensions is good, but actually 3 dimensions is better. So now just go and get the molecules. So what I've done now is I've gone and got the molecules, getting the molecules from Germany, because this is where it's running. Come on, molecules, you want to come into my notebook. They're trudging their way across the internet as we speak. This is where my Wi-Fi kills me. Come on, molecules, you can come into my notebook. There we are. And this is actually at least 7 seconds ago what the molecules were like when they were first sent. And we can then begin to visualize them and interact with them. Now, the data that's being produced on that simulation is sitting on the cloud. As you just saw, I've just brought my visualization to my laptop, which took a bit of time. But the data's on the cloud. I should have the compute running on the cloud as well next to the data. And that's what this is doing. The data's being put on the cloud. Is a trajectory of this molecule as it evolves through time. There's been 7 frames of it. And what I can do here is I'm basically getting a handle to those frames and then asking it to go and run an analysis on the cloud of a typical type of analysis that you would do if you're doing these kind of molecular simulations. Again, this is what I call serverless. As a researcher, I haven't had to think about where everything's been happening. I'm interacting in the space of the researcher thinking about these particular simulations. So I just play from current slide. Hopefully this will come back up. Magic of the laptop. Interfacing laptops and displays is always the hardest thing ever. If someone could solve this problem, I'll be very happy. So that was the demo. And basically, Jupyter notebooks, they're fantastic. They're taking over, I would say, life sciences, medical sciences, even physics, chemistry, machine learning, data science, etc. And it's because in one web-based notebook, you describe the experiment. You have the code to run the experiment. You have all of the code to analyze it. You have all the 2D visualization of the graphs, the 3D visualization of the molecules. They contain everything needed to publish and reproduce that particular computational experiment. And what's more, because all of the data is sitting with the notebook and all the compute is happening with the notebook, it means we don't have to begin moving data backwards and forwards around the planet. It effectively means everything is happening together. And when I render something, the only thing that needs to come back to my laptop is the renderable. So this is actually just a video of me rendering a massive molecule to just show you it working between my home Wi-Fi in Bristol, and that was a server that was happening to be in the US. And it's completely fine. Now, notebooks are useful because, as I said, they're useful because they can be published. Effectively, what we have here is an open, reproducible, executable scientific paper, but they're only useful if we can actually put them on the web and have people use them, if there's some compute sitting behind them. So how do we do the compute? This is where Kubernetes comes to our rescue. We run Jupyter notebooks using Jupyter Hub, which is run on top of Kubernetes. Jupyter Hub is completely open. It is distributed as a Helm chart, and literally you just Helm install Jupyter Hub. It's that simple. It runs on top of all of the certified Kubernetes clusters, so I've run it on top of Microsoft Azure, Google GCP, Oracle OCI, etc., and it is great. But there is one major problem when we're trying to run these kind of workloads on top of Kubernetes, and that's that our Kubernetes cluster is basically provisioned to run the notebook. So it has lots of small VMs that are ready to serve little Python kernels which are serving each notebook. But I want to do things like run massive simulations. Those massive simulations need a lot of compute power, more compute power than my Kubernetes cluster can basically provision. So I need another mechanism through which I can burst out of my Kubernetes cluster, grab hold of some big iron compute, and run the simulation over there. And the way we do this is using FN, which is an open source serverless framework. Effectively, this line here, which was the md.run, that is not bursting it within the Kubernetes cluster. What that's doing is calling an HTTP endpoint, which is then creating the resource for a large HPC cluster, transmitting the data to that cluster, and then running it on that resource. So we've burst out of Kubernetes into a separate resource here. And we have to do this, as I said, because you can't really do that kind of bursting by starting a new Kubernetes pod. Now, FN might be new to some people, so I'm just going to have a quick overview of what FN is. FN is an open source event-driven functions as a service platform. It's completely open source. I've run it on most of the clouds. It's a fantastic thing, and the unit of abstraction is the Docker container. So actually, when Kelsey was talking this morning about, I want a Docker container, have standard in, run a Fortran program, and write standard output, that is FN, and that's what we do live all the time now. So effectively, what you do is you package up everything you need into a Docker container. The HTTP request comes in and is interpreted in the container as standard in. You do whatever you want with it, with the standard in, running whatever program, whatever language, whatever legacy apps you have are processing standard in. Anything that's written to standard output is what's returned by the function over HTTP, and anything you write on standard error goes to log. It's really simple. So just to remind you, any code and all of the associated programs and all of your libraries and all your installation, the whole lot goes in the container. HTTP request goes in as standard in. It's run in the container and interpreted normally. Standard out gives you the output. Standard error goes to logs. Now, the nice thing is when you call these HTTP endpoints, they can either be synchronous functions or asynchronous functions. So if I call a synchronous function, it will run immediately, and you'll block until you get the return value. With an asynchronous function, it runs immediately, but immediately returns a call ID, so that then you can basically just leave it running. Because we're talking about functions here that are simulations. These could be functions which are running for a week. This is not your 5-millisecond function. Now, as I said, it supports any language, because it's whatever you want to put in the Docker container that can read standard input, which is like everything. But there are function development kits that can make it a bit easier to do all of the serializing to and from JSON if you want to be more standard. And so I tend to use the Python development kit, which is called the FN development kit FDK. And this is actually the hello world example for FN. So effectively, what will come in is a post request, and I'm posting name is Chris. FN has basically serialized that into a JSON string, name is Chris. And then in here, and I apologize, this is small, I thought the screen would be bigger. Effectively, what's happening is it's just calling a function that's taking the JSON out, and then just printing out another JSON string, which is hello Chris, which then comes out as the output. Now, this is a toy example. And I think in all the talks I kind of see when people talk about serverless, they always talk about toy examples, uploading things to Twitter or doing some basic things. We do more than that. So effectively, that md.run, which is running the simulation, that's going to do an async function call across to a Docker container, which is then started on a big HPC node. And that Docker container contains the GROMACS application, which is essentially a big C++ application for doing dynamics. It contains a small Python script, which basically takes in the JSON, parses it, then starts the GROMACS process, and then it just runs as an async call. Now, obviously, at this point, you're thinking, crumbs, you're doing a function call here, and you're passing in the arguments of this function call distributed are all of the molecules of the system and the protocol. This could be a really big argument list, like megabytes or gigabytes of data here. And obviously, that would be really hard to serialize to JSON. I've had people who want to serialize it to JSON, but that's a really bad idea. So instead, what you do is the obvious thing, and that's you copy the data to an object store, put it in a bucket. And when you do the function call, you just basically pass in the bucket in which the data's got, and the data is copied then into the container which is running the function. But what about the output? What we have running in the background in the container is a little Python server, about 200 lines, and that's using Watchdog. And every time there's a bit of file that's being written by the program, that bit of file is streamed live back into the output part of the bucket of the object store. This means that live, my notebook can basically query the object store and get the data. Effectively, this is your POSIX to object interface. Simulations run in POSIX. Object is used for distribution of data around the planet. So this is great. You can have different molecular dynamics programs behind different functions. We can use different functions to refer to different bits of hardware. So I can call a GPU function or a CPU function. I can have many different types of scientific application behind this. And because the FN framework is open source and cross-platform, I can deploy these on every single cloud. Life is good. And this will basically work with any application. And all of the data is live going into object store, which means already the output is globally accessible. I can give a URL or a DOI to that particular bucket, and immediately I can publish my results. This is fantastic. I have a great framework that allows anyone, anywhere in the world to run HPC simulations just by calling an HTTP endpoint. Oh dear. Anyone can run simulations by calling one of my HTTP endpoints. I'm going to be poor, because if I publish that endpoint, scientists are quite cunning. They will find that endpoint and they will start throwing simulations at it and get lots of free compute. So essentially, we need a way of not just making this something which is kind of like an academic toy. There has to be a business model around it, which means you need to have identity management, authorization, and accounting, and that's exactly what we built. We built an identity management, multi-cloud accounting, and access management service discovery system that's actually built on top of FN as well. So effectively here, I hope this is readable. What you have is basically, it's all interfaced. For HTTP endpoints, it could be with anything, but this is actually all going through Jupyter. And effectively in a Jupyter notebook, you're logging in. And when you log in with the request to login, effectively that's calling an FN function, passing in as argument the session keys and the session certificates for that particular login session, and the return is a URL, which is then used for out-of-band login, which is turned into a QR code, which you can then scan on your phone, or you can just go to, which then brings a web page to put in your credentials. The web page as well is an FN function. So FN can return JSON, but it can also return HTML. So it means that then you call the function to do login, you put in your password and username and the one-time code, and it's all processed as a single FN function. So I'm just going to run that through. So you can see here I've put the login in, requested the login, it's given me back the QR code, then we click onto the page to get the login page, and then I put in my username, password, and because this was a device that's already recognized, I didn't need to use Google Authenticator to log in, and voila, it's now logged in, and your scripts can be left paused while it's waiting for the login to happen. Now this is great because it means that it's completely distributed. I don't need to have a login server running all of the time. And as many people who want to log in, it will just fire up more and more functions as necessary to handle the load. Now, while that all works, for login, we need to do the same thing for other services. So what we actually have is step one, you've got login, which is run through an identity service. You then have an access service, which is used for service discovery to say, I've logged in, now tell me what I have access to. Then we have an accounting service, which is basically full double entry bookkeeping, and we work with the cloud companies to work out how we're going to be actually doing accounting across clouds, so a researcher can basically run from multiple cloud accounts. We then have the object store and gaining access to that to place data and publish it around the world, and then we have the simulation function store and function service for then running simulations. And what you can see here is I've actually drawn them all separated. And that's because every one of these services is completely isolated. They're separate from each other. They're all independent function services running on top of their own FN instance. And indeed, they're in different clouds, and they can be in different clouds. And indeed, it means I can have multiple of them. So I've drawn one of them, but we can have 10 identity services on 10 different clouds. You can have 10 accounting services. And we're building a completely distributed system for logging onto clouds, running simulations, accounting, and doing all of that work. And it's all because serverless is enabling us not to run resource permanently. Effectively, if no one's logging in, there's nothing running. But as soon as people start logging in, it just automatically scales in a distributed manner to handle everything. Serverless is brilliant. Serverless solves everything. So I'm sure you've probably heard serverless, 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 serverless. You should all move to serverless. Life is perfect in serverless. Isn't it wonderful over there, the land of unicorns and rainbows? And of course it's not. We always go through, I mean, I'm old enough that I've been through so many tech cycles going backwards and forwards. Edge, cloud, how many times are we going to keep doing that? Serverless, managed services, it's just all the time. And of course, serverless has many issues. The biggest issue that I hate the most is cold start. Who here hates cold start if they've used serverless platforms? Okay, show of hands, what is an acceptable cold start? So are you willing to wait 10 seconds for your function to start? So hands up if you're willing to wait 10 seconds for your function to start. Okay, you're quite good. 5 seconds? 1 second? You're way too tolerant. I want milliseconds. So basically, this is terrible. This is me running a function twice. The first time it ran, it basically came up in 4 seconds. The next time it ran, it came up in 90 milliseconds. Now, I code HPC machines. I'm writing code which is basically vectorized, parallelized, gets every last drop of performance out of these wonderful things that Intel and AMD and others have created. And in 4 seconds, I could do 400 billion floating point calculations. I can simulate picoseconds of dynamics. I can begin to, end world hunger in 4 seconds with some simulations. And you want me to wait that time for one function to start? I mean, I think even functions started quicker back in the 1970s on the original mainframes. This is not progress. And of course, you'll say to me, yes, Chris, yes. It takes a long time because the container has to be allocated. You need to start your runtime in the function. You need to import your modules. You must run the script. These are stateless, so we need to reload and unload the state, blah, 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 blah. But don't worry, because we'll keep it hanging around. So once you've done a cold start once, you have a little bit of time afterwards and the function will be hot and you won't pay it again. Hence why first time 4 seconds, next time 90 milliseconds. Now, while you all think that that means it's great, we've solved the problem because we keep it hot, it's not. People are paying cold start. You've got to eliminate cold start because I'm calling functions that call functions that call functions that call functions. If each of them has a 1 second cold start, that's 10 seconds potentially that I'm waiting, spinning my wheels, doing nothing. So the first thing I do to get rid of cold start is let's not have a cold start for every single function in my application. So what we do is we bundle all of the functions together into one container. This means that the actual function I want to call is effectively an argument that's being called. So here, this is a really stupid example, but effectively here there are two functions, hello and goodbye. And so when I call the function, I pass in the argument, which is in this case Chris, but we also pass in the function name. And so if we're asking for function hello, it calls hello. If we ask for function goodbye, it calls goodbye. Very simple. This is the bundle we use for the identity service. And effectively what goes in here is the JSON request saying, I want to call the function request login. This is the username, and I'm of course not going to tell you my public key and things because it's generated at the time. And because it's asked for the request login, it calls the request login function, and the rest of the functions are ignored. Now the beauty of bundling all the functions together into one container is that once that container goes hot, all of the functions are hot. So I only pay that cold start time once for the whole bundle of functions. Equally, that container, once it's been pulled onto the node, all of the functions are now on the node. I'm not going to be pulling 100 containers from my 100 functions, because if you do serverless properly, you'll end up with large numbers of functions. So bundling them all together into single containers, small containers, it enables you to basically get rid of some of that startup time through working. Now, the other thing it does, as well as enabling one goes hot, they all go hot, plus one's on the node, they're all on the node, is we say that functions are stateless, but actually there's a lot of state, which is really useful to cache between calls. State, which we know does not change between those calls. So for example, I need to log onto the object store and get data and know who I am. Once I've got that data and got those IAM credentials, etc., I should not be getting them every time the function is called. I should be caching them between the calls because it does not change. Equally, there's data in the object store which is read-only, which is cacheable data. So once I've read those keys, I don't have to read that again. I'll just hold that within the actual function. And then because we're using asynchronous Python, the actual functions event loop is an asynchronous event loop. This means that that one event loop can actually serve multiple functions at once. So rather than have one event loop per function, we now have one event loop for the whole bundle of functions. Now, all this has done is basically reduce the number of cold starts we're going to have and reduce the amount of reloading things that we know are not going to change. It hasn't actually got rid of cold start. To get rid of cold start, you really need to profile your applications. So you need to say, where is the time being lost? And remember, I like milliseconds. I'm not happy with seconds. So step one, we didn't program anything in Java. Sorry, Java developers. But if you look at Python here, this is literally the time to import JSON in Python and start Python and then shut down the Python interpreter, and that's 61 milliseconds. That's fast enough to actually be used as a runtime for a function service. I'm sure Go and others will be just as fast. But there are modules that you need to load when you're running your function, and those modules, some of them can be really slow, but of course you don't know what they are until you profile them. So again, profile your application, profile your import. So for example here, profiling in Python is really, really easy. You just set an environment variable, and then it will profile all your inputs, write an output file that can be processed via tuner, and in these 2 lines you get a beautiful icicle plot that tells you that this module we've imported here, OCI, apologies Oracle, that module took 1.4 seconds to import. I'm sorry, that's shocking. It should not take 1.4 seconds to import a module or a library. Again, these machines do hundreds of billions of calculations per second. Always remember that when you think a second is short. It's not. Hundreds of billions of calculations. Now, the reason that took 1.4 seconds to import was because it was importing everything that could ever possibly be used by that module in the whole of time. And of course, I'm running a function, I only need certain functionality out of it. So the way you solve it is you actually use try import. So try import is basically a little mechanism in Python where instead of importing something, it will import a handle to it, and only when you use it will it actually import it. And so I went into the init.py of OCI, and I changed every single one of their imports into try imports. And that was the extent. This little black line, you see 10 lines of code here, that was all I did. That took about profile 5 minutes, change those lines of code another 5 minutes. And you probably can't see the numbers here, but that changed the OCI import from taking 1.4 seconds to 37 milliseconds. 20 minutes of my time to stop 1.4 seconds of pain for every single person who loads this. As developers and engineers, we should do this. So profile your code, profile your imports, profile your functions, then you will basically begin to eliminate the cost, and you only pay the cost that you need. But then I'm now going to say something that some of you may disagree with. We shouldn't pay cold start time at all. So as well as writing software and doing all that stuff, my other life is I actually design and build university supercomputers. And when I build a supercomputer and I have a compute node, I buy 2 power supplies for that compute node. Why? Because if one of them fails, I don't want to pay the cold start time of phoning up the supplier and waiting them to deliver me a brand new compute power supply and then installing it. I want to have another second backup, one hot spare, ready to take over immediately. And I think in the functions world, we cling on to this idea that we're scaling to 0 and that you shouldn't be paying anything when it's not running. And what I'm telling you is actually you should scale to 1. You should always have one function running all of the time, and then when that function is being called, that function should spin up one hot spare. And so here you can see in this, when I'm calling request login, there's actually an async function call going at the same time across to warm. And what that is doing is basically spinning up a hot spare so that that's then ready in case more people come in at this point. Now, all of this is not serverless manifesto. I've bundled independent functions into one block. I'm spinning up things and having them run all of the time. I'm paying for stuff that people aren't using because it's running idle. But let's remember here, these are things running effectively on one-core VMs, particularly for the identity service. Those one-core VMs cost me approximately 1 cent per hour. Is the principle of serverless manifesto really worth saving 25 cents per day, about $1 something a week, forcing people to have cold start times? It's not. Practicality always beats, pragmatism always beats idealism. I think we need to move away from the cost benefits of serverless and instead say, actually, let's build systems which are distributed and where people don't pay cold start. We engineer them so they're always ready to help people. Now, effectively, what we've got here, and the way I like to think about this, is we're building now systems where simulations and data and logons and notebooks are now happening all over the world. And as a scientist, as a researcher, I don't have to think about where all of that's happening. It's a bit like, effectively, we're programming what I call the planetary supercomputer. So if you think of when you program a normal computer, you've got a console GUI and you've got memory storage and you've got processors and things like that. If we think of all of the clouds together as one big planetary supercomputer, then your object store is effectively disk and memory. Those functions that we're running are effectively processors. The Jupyter Notebook is effectively your console stroke GUI. And then if you think about this sort of authentication system we're building, that's basically user accounts and resource management. Building a world where we can build applications and deploy them on the global planetary supercomputer and just have people use them without ever thinking about where anything is, that's what I think serverless is. My students don't call it planetary supercomputer. They think it's too cheesy. They call it the Netflix of simulation, because they like the idea of just streaming simulations on demand. And again, they don't think about where the files are. They don't think about what servers they're using when they're watching their shows. They don't care about the infrastructure. They definitely should not be running a kubectl command to Netflix and chill that night. That is not what they should be doing. And the same for researchers. We should be working on the parts that have value. And just to demonstrate this is a planetary supercomputer, What you have here is basically the login steps working, where essentially the notebooks are in Seattle. The one on the left is basically FN running on Google in Japan. Middle is Azure in the Netherlands, and then the right is basically OCI in Germany, and the data is actually held on an object store, which is notionally in Germany, but obviously they do optimization. Effectively, you have this global thing now, and this was all running again from Seattle. This is real time in terms of the movies. Obviously, it's movies because I didn't trust the Wi-Fi, but it's that quick. It's really nice. So I'm just going to finish and acknowledge. Obviously, I've got a big team helping me. When I say big, I mean tiny, which is basically my research software engineers. We get funding from the government. I'm so lucky that I get funding from the government to play with cool things and to think of the big problems. We don't get paid much in science, but we get this warm, fuzzy feeling of knowing that we're making the world better and not selling stuff to people. Sorry. I really want to thank basically the cloud sponsors, so basically Google, Oracle, Microsoft. They've all been massively helpful. So they've been giving us cloud credits, but more importantly, we've been sat down with their engineers and saying to them, actually, how can we build a planetary supercomputer? What do we need to do to enable multi-cloud accounting, multi-cloud movements of data and compute? And we think there's this huge future where essentially you have researchers creating these workloads and throwing functions up, and there's this big space for the cloud companies to compete on how well they can move the compute to the data. Because actually on the simple case, when you're thinking about the data's here and the compute's there, well actually maybe it's better for them to run the compute in here in America at nighttime when there's less load, and so let's move the data to America in the back end. There's a huge amount of ops that could go on underneath that would be really cool. So with that, thank you all for listening to my talk, conference people for accepting me, and I am happy to answer any questions. Thank you. Okay, I'll go with the person at the back. Okay, so the question is basically, how can I scale when everything is all in one container? So what am I doing from the Kubernetes perspective for that? The scaling on HPC is not within Kubernetes. So when we do the call, the FN call to run the simulation, that FN call basically goes across to a functions service and says, I need this resource from the function service, and then puts the container onto that. So that means that the resource, which is for Kubernetes running Jupyter, is just VMs. It just doesn't need to be much. But then dynamically, we provision the hardware, the HPC hardware that we need to run the simulations as an FN function call. And it's the FN service which basically manages that. So the question is, what is try-import? So try-import is basically, it's a little module in Python which you can put in. So you import try-import, and then all you have to do is, rather than say import module, you say object equals try-import string, which is the name of the module, and it returns a handle to the module, and the first time that handle is used, it then does the import for real. So it enables, effectively, you don't do it on your top level dependencies, you do it on your second level dependencies, and that way the dependencies don't just spiral out and import everything, they just pick the bits you actually need. Was that okay? Excellent. Next. Oh, doing triple question here, go on. So I've not considered Zeppelin, I'm afraid. I know very little about. So the question was, did I consider Zeppelin instead of Jupyter? I'm afraid I've not considered Zeppelin because I've not played with it much. Essentially, in universities, at least in the UK, Jupyter has won. It's the thing that's used by everybody. So that's the environment we teach in. It's the environment they're familiar with, so we stuck with that. Okay, go over there. So the question is, who launches the HPC cluster? That HPC cluster is basically launched by FN in the cloud. as bare metal. So with OCI, one of the nice things they've got is it's a completely bare metal cloud with a hypervisor effectively as hardware in the switch. And so the actual hardware nodes, they're ridiculously beefy nodes anyway, but the network connection between them is as fast as InfiniBand. And indeed, from the specs, faster than InfiniBand. So you get these really nice HPC clusters that can run big workloads. You can either go through FN, but the other thing we're playing with is essentially doing backends, which use what are called instance pools. So we started with Terraform to bring things up and down, but now there's basically an instance pool interface, which will make it a bit easier for us. So there's a lot of plumbing underneath, which I didn't talk about. But again, scientists shouldn't think of the plumbing. It should be completely transparent to them.
And this is on AWS bare metal.
On OCI, Oracle Cloud, bare metal instances. Yeah. I'm afraid I haven't run anything on AWS. If an AWS person wants to talk to me, I'd be happy to talk to them. Yeah.
So are these simulations running multi-core? Basically, my question is, let's support running MPI kind of job.
So the question is, are the simulations running multi-node MPI kind of jobs? And the ones I demonstrated were not, because the nodes we run on already had 104 cores. And so essentially didn't need to. It's ridiculous, actually, the HPC node shapes, particularly with the AMD EPYC, they're huge. But they can run multi-node, so we have some multi-node tests that we've run, because ultimately, all you're doing with the function call is saying, give me this resource. It gives you the resource, and then you just run it. And so you can ask for, and when it's running on bare metal, it doesn't know it's been provisioned this way.
But who's taking care of the communication between the jobs? Or the same job?
For the same job, basically, you've spun up 4 nodes. It spins up the MPI daemon, and then those 4 nodes are basically talking to each other through MPI. Okay. Any other questions? Go ahead. Yeah. So the question was, if they wanted to use TensorFlow or Kubeflow with this kind of integration, could it go that way? I don't know enough about how Kubeflow works. What I would say is if you were looking at the identity management authorization, the sort of JWT tokens for that, we could probably reuse those bits. And ultimately, all of this is just HTTP endpoints. So in theory, you could just be calling those points and working with them. Okay.
Are you coming to the academic lunch?
I did not. So the question, am I going to the academic lunch? I've actually not met any other academics at this conference yet, because there was one academic at this conference so far. I didn't know there was an academic lunch. When is the academic lunch?
No.
Okay, I will probably be going to the academic lunch. Go on.
Everyone is invited to the academic lunch, by the way. It's just downstairs in Skagit.
Excellent. I look forward to, as long as there's vegetarian food, I will be happy.
There should be.
Perfect. Yeah. So the question is, 2 questions. One is the AAAI stuff open source? Yes, 100%. I'm an academic. Everything we do is on GitHub live, so you can see all of our bugs as we're developing them. And it is open source. It's Apache licensed, because we really want it to be sort of very usable by lots of universities, and we're thinking of how we can move this into a national system. The second question, sorry, I forgot. Can you repeat? So how often, so the question is, how often can you update the FN wrapper, the little Python script which runs the workflow, and how easy is that? And it's actually, we update it quite a lot. So the wrapper we're talking about, the reason we can build this thing quickly is this is not millions of lines of code. It's like a few 100 to 1,000 lines of Python. It's really simple. And FN has this really brilliant developer interface that effectively, once you've got your Docker file to describe the container, you just go FN build, FN deploy, and then the whole thing just goes up. So I probably deploy functions live dozens of times a day. And when you deploy it to the service, it just goes on to the next newest version. So as a developer experience, it's really brilliant.
What sort of data volumes are your researchers moving around?
What sort of data volumes are my researchers moving around? We live in the peta to exa world. So effectively, you can be having, like the simulation for, so I showed, the small demo was just like tens of megabytes, just because I wanted to do a small demo. But in terms of the real simulations, those are tens of gigabytes to terabytes to petabytes of data. And so one of the things we're building, so we've architected and are building next year from February, is effectively, indeed I can show a little picture of it, is a system where effectively we're taking all of the UK satellite data and all of the atmospheric sensor data, and that's all being piped in this framework here into object stores using FN functions doing cleaning of the data, using FN functions to do analysis, Jupyter notebooks to enable interaction from researchers and also from the public. And you do things like, we've detected this cloud of methane here, we now spin off CFD calculations that can backtrack the methane back to the individual cows. The purpose being is in the UK for the climate change report, we need to count how many cows and cars and trains and buses we have. So all of this will just be spun up, and we're building this next year. And again, if there's anyone here who would like to work on this project, I'll be hiring in January. Again, the pay's not good, but you're helping save the world and not sell stuff, so that's kind of cool.
Yes, you mentioned scale for one. So how aggressively have you set function up to clean up after itself? Scales very rapidly, creates new nodes.
So how quickly is function set up to clean up after itself? It's really aggressive. So basically, FN scales back, so it goes from hot to cold after about 10 seconds. And so that's why cold starts really hit me, and I haven't worked out how to change that. It's buried in the code.
And that includes the deallocation of the VMs from the cloud provider, et cetera.
That's the full deallocation of everything that it's working on, yes.
Have you done anything with like restricted data, or are working towards being able to handle things like restricted data? I'm thinking like patient data.
Yes, so we have a project which will be starting off with basically EBI, which is looking at patient data and gene data. And again, the discussions with the cloud companies are, you actually have object stores. The object store data, when I talked about, oh, you could publish it, there are obviously full ACLs on that. All of the data in this entire system, we built all of it to handle private data. So everything is massively encrypted, massively secure, one-time passwords on everything. Data is encrypted on flight with neutron passwords. Data on the object store is encrypted on rest with rotating passwords. All of the cloud companies now ISO certified for data compliance. And indeed, I think if anyone comes from the UK, you know that we're moving all of our NHS data on the cloud. So I personally think that it's a governance thing. It's not a technical thing anymore.
Can you share your code on GitHub?
The code is on GitHub.
The
repo, I shouldn't show you that bit. The repo is basically github.com, then /Chris Woods, and then it's called Choir. And if I try and make that bigger, yeah, you should be able to see that. And that's basically for the accounting and infrastructure part, which we forked out. Yes?
Second question, have you tried running like a super scalable API using something like Python Flask and like handle massive amounts of just inflow data?
So the question is how I use Python Flask to handle massive amounts of inflow data. No, I haven't, and I think that would be really interesting. So again, it's kind of like, in the academic world, we've looked at the cloud a bit like we're scared of it, that we don't want to lose our precious HPC machines. And I've built machines for a long time, as I said, and I've reached the point where I never want to buy another cluster. I never want to install another cluster. I never want to deal with another cluster. I just want to throw things in the cloud. And the nice thing about the cloud is when you move beyond it's just a cluster and actually view it as a planetary supercomputer where things are just flying everywhere and it infinitely scales, blah, 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 you actually begin coming up with these kind of ideas and you say, actually, there's a whole different way we could be doing computing, which technology is not the point. Because we can do the computing this way, interactively, live cycle, we just speed up the innovation cycle and we solve problems better. Because ultimately, we want to science the hell out of it.
Okay, but there are just lots of use cases where you're tracking all kinds of metrics.
Yeah.
When you're trying to sell things.
Yeah, you can do it for selling as well. Go on.
When you first showed the notebook, that first line, that was like .ng or...
Yeah, I can go back to which line.
That actually calls out to your system that set up the...
So this one that runs the simulation, or this one that's setting the protocol?
So that is the thing that's making some asynchronous HTTP call to your backend to say run this
Yes, so effectively what that call does is it goes, here I have my data, I copy the data into an object store, get the bucket location for that data, and then I call an HTTP endpoint, which is calling the function, tell it the name of the bucket, and then I get a call ID back.
And is it sending this notebook?
No, it's sending just the data, which is for that molecular simulation. So it's not the notebook that's gone across, it's actually the molecules. So it's these 631 molecules here that have been loaded, plus this protocol for how you run the simulation effectively. That's just turned into the input files for running the program. So we don't need to send that much. It's as much as information as the simulation has. One of the interesting things is at the moment, this is actually running, the data is already on the notebook, but we want to then move to a world where you start off with the data on the laptop, and then you move the data onto a notebook, or you move the data up to somewhere. And this is where we now need to think of what's the metaphor for where data is. Because researchers, again, they're used to, I've got data on my laptop, and what's the right metaphor for thinking actually it's here or here or here? And I don't think it's a file system. I do think it's a way of playing with objects and buckets. And we know it works because effectively when you use Google Photos, you don't really think about where anything is. And we need that kind of similar interface for genes and simulations and CFD runs and things like that. And again, I'm interested in people's ideas of how that could be. Do you have any other questions? Okay, so this is a very good question. Have I compared this to Lambda? And there are two aspects of my answer to this. One of them is that as a researcher, I've got to build on top of open portable platforms. So we were bit really hard when we all made stuff with CUDA, and we ended up being trapped into buying lots of NVIDIA hardware. And because of that, there's basically a moratorium on you will not go and use a single vendor platform. So we have to go on open platforms. We cannot use AWS Lambda and design for that. That's one of the reasons we went to FN, because it's open and portable and we can move it between clouds and it's no problem. The second reason is because the unit of abstraction should be the Docker container. So the problem with Lambda, I think, as Kelsey's talk showed, you can kind of create a zip file that contains a static application, and you can work really hard to do that. But actually, most scientific applications are not one static zip file. It's a much more complicated environment, including your MPI drivers, maybe your GPU drivers, all of these extra bits and pieces, this huge application that you cannot just put into a zip file. You can put it into a Docker container. And so the unit of at least scientific serverless has to be a Docker container. And the easiest way for us to get things in and out and understand it is standard in, standard output, and standard out for logs. So I think if we build serverless frameworks with Docker container as the root, standard in, standard out, I think it would be perfect. And any serverless framework which has that as its root, I'm happy to move to. And if AWS would like to move to that, I think it would be great. Ideally, what I'd like to see is, because there is already FN and it works so perfectly, that all the clouds go, let's go and use managed FN services, rather than I mean, Knative looks good, but it's so far behind where FN is. You know, being blunt, FN is really working well. Oracle are launching their they've announced their production FN service a few days ago. So at the moment, I'm running my own FN clusters on top of Kubernetes, but eventually I should be able to just buy them and not have to care about the underlying Kubernetes clusters. Any other questions, or are people hungry? Because I've heard an academic lunch is somewhere, and I'm a researcher, so I would go for lunch.
It's the floor under the main floor. You just where the front doors are, you just walk back and there's stairs down.
I will follow you. That sounds good. Thank you very much for coming. Thank you for your questions.